is in some situations, your body has to help you out and not constantly let fluid come out of your body. So we have to understand this whole concept. You've got to remember this concentration gradient to describe this. So here, this was the essay, I said I'll give you a diagram in here of that information. It's not going to be this one though. I think you guys decided if you get this essay, that you want this diagram.
Yeah.
All right, and that works better for me because you have to tell me those numbers rather than me giving them to you, and that's okay. So here, you've got to remember what's going on in this loop, which was the diagram I showed you just before. So the loop of Henle, in one way, is going to help you because what you have is you have permeability to salt on the ascending limb. The descending limb is permeable to water. So you got that little dynamic going on there, and then you got this distal convoluted tubule and the collecting duct that during regular drinking, where you're in that normal range, and you've got to tell me, it'll say, what is the normal range that you would normally produce dilute urine is, and that's between 285 and 300. If you're in that range and you keep drinking, your urine's gonna look like this. Sometimes if you start creeping up a little bit in the 295, you might get a little ADH produced and released. Here, not so much because you're dehydrating, but you're moving out on the thing. So at some times, your urine may look a little stronger. Certainly when you get out to 300, you're sending off alarm bells that now you're losing a lot of water and you're up on the high side, so you gotta stop your body, and your hypothalamus monitoring that blood osmolality is gonna stop you from having that problem. It's gonna try to make you drink, but you may not be able to do that. So now it's gonna say, all right, I'll stop you from dehydrating quickly and buy you some time to do that. So every time you urinate, when you get over 300, your urine is gonna get darker and darker and darker. There'll be less of it as you go, reflecting the amount of ADH that was released and your corresponding response to that. So remember we said that ADH was produced by the hypothalamus, by those neurosecretory cells. You gotta put that in there. And then as it circulates through your blood, it's gonna get stored in the posterior pituitary gland to be released when the hypothalamus directs it to be released. It gets released, it'll have its effect then on the distal convoluted tubule principal cells, as well as the collecting ducts. Here, what it does is it changes their permeability. Normally, they're impermeable to this. So here you can see, here's the concentration when you get deep in the medulla, and you come back up here, and now it's back to its 300 milliosmoles, more or less. And then as it starts to enter down it through that gauntlet of increasing concentrations of salt, in an impermeable tube, there's no influence on that. So that fluid, if it was 300 up here or 280, it's gonna come right out of there and it's gonna be dilute urine. Once you have ADH present and it binds to the receptors on those principal cells, you have those aquaporins 2 channels. And the aquaporins 2 channels is a membrane channel that's gonna be in there, and normally it's not on that surface, and that gives you your impermeability. That's actually gonna connect up to this and now give the ability to get fluid through that tubule into the kidney proper, into that kidney tissue. As it's going down there, now it's subject to very high concentrations, maximizing at 1200 milliosmol. So as it's coming down here, and this diagram is kind of trying to show you that it's getting more and more concentrated until it gets down here, and now you have a little drop that's yellow because it's much more concentrated than it would have been. So that's the concentration mechanism. How is it then that you don't wind up diluting out that medulla with all this water? Well, the answer to that is not to be had on this diagram, so you'll have to remember this, but the answer was on that other diagram, which is, I was surprised me why you didn't want that one, which is this one, which is the vasa recta. And we said they're just separating them on this book to show you how this is, but this normally sits right in here. So what happens is you have this constant cycling of salt, you have the constant cycling of salt and water over here to maintain this concentration gradient. As long as you maintain this concentration gradient, then every time you have ADH present up here, you will suck that water out of there, and then you'll balance that with the salt that's coming out of here, as well as the water that gets reabsorbed by the loop of Henle. And this whole process of maintaining that is brought to you via that vasa recta. You couldn't do that without the vasa recta having that salt exchange. And that process is called this countercurrent multiplier system, because what you have here is this constant dilution here, and then the constant turnover and replacement of that salt and the removal of that water by the loop of Henle. That's what maintains this gradient. So then, at any time after that, if you drink and you are within that normal range, you do not have ADH released, and everything goes along great. Every time you have to go to the bathroom because you're filtering blood constantly, you go there, you urinate, and it's relatively clear urine, a little yellowish tinge, and that's urobilin. Then we said that if you get a little dehydrated, if you get a little dehydrated, then your body's going to release proportional ADH, and then you're going to start concentrating urine proportional to the release of how much hormone was there. If we went on a camping trip, and now I forgot to bring the water, and all of a sudden, after a day or two, everybody's way over 300, and you're all complaining and yelling and arguing. That's all because you're getting more dehydrated, but if everybody looked at their urine, if I also brought the little urine samples with me, and you guys could determine your own urine osmolalities, everybody's urine osmolalities would be very high because you're concentrating that urine. There's a limit to that, and you can only concentrate so much urine. At that point, your vascular system will collapse and you won't be able to concentrate urine, and you'll die. And that's right around 330 milliosmoles. If you get up that high, you'll be on someone's morgue table. And all the hypothalamus can help you on the other side is if you drink, you can have the exact same problems. It's only now your kidney can't help you. Your kidney can only filter as fast as it can filter, and you'll have dilute urine. But you keep drinking faster than you can filter, and now your blood osmolality is going to get less. If it gets too less, you can die from that. And that's that lady that was, I told you on that show, that radio show where they had some prize that she could win if she could drink so many liters of water in less than an hour. And she got herself water toxicity. And the hypothalamus can only communicate to your brain and say, stop drinking. And she did that. She's told this guy, she's, look, I don't feel too good. I don't feel like doing it. Oh, you're almost there. You only have 2 more bottles. And then she gave in to that. And when she did that, she drank too much fluid and she died.
Wow. That's crazy.
So that's the situation. So the model of this is bring water with you when you go camping and you go hiking.